Good afternoon from here in Paris. Thank you for joining us for today's Siemens Global webinar. My name is Caroline and I will be your host for this event. Thank you all for joining. Today's topic, we will be looking at product development, automotive supply chain, aftermarket. I am delighted to welcome as our speakers today, Mr. David Chadwick and Mr. Craig Hall. So I will give a very brief bio of the speakers and we will be ready to start. David is a business development manager at Siemens Digital Industries software and is focused on industry solutions from the solid edge portfolio. David has 30 years of application engineering, project management, and marketing experience and has been involved in many successful PLM implementations in small and medium-sized manufacturing organizations globally. Craig is a small business owner offering design and procurement services to the leading race car builders in the off-road racing industry. Craig has 20 years experience in the sheet metal fabrication industry, tailoring to motorsport. Craig's race car designs have led to multiple race victories, including the Baja 500 and the Baja 1000 and the win at Dakar. All right, so without further ado, I would like to hand over to our first speaker, Sir David Chadwick.
Thank you, and it's great to have this opportunity to talk to you today about speeding product development for automotive aftermarket and supply chain manufacturers. We will first talk about the trends that we see impacting these industry sectors and discuss the implications of these trends and some possibilities for reacting to them. We will also talk about recent advances in engineering software that make it easier for all manufacturers to participate in a digital transformation, creating a digital twin of their products and using this throughout the product development process. There are many technologies and software solutions that enable this concept of a digital twin. Today, we will focus on just a few of these and give some examples of how our users are succeeding. I'll then hand over to Craig from Hall Designs for his presentation of a design through manufacturing project. Hall Designs is an excellent example of a smaller company that is implementing the digital twin concept to create solutions for their customers in the area of off-road race vehicles. When we look at the automotive aftermarket and supply chain sector, we see that manufacturers worldwide are facing similar challenges. The first trend we will discuss is a growing global and local demand for automotive aftermarket parts. This research from McKinsey predicts that the automotive aftermarket business will see steady growth over the next decade. Today, North America is the biggest revenue area by zone, closely followed by Europe, but McKinsey sees that Asia as being the biggest driver of future growth. They also note that the automotive aftermarket sector will be significantly impacted by new trends in the areas of electric vehicles, connectivity, and autonomous vehicles. The research also found, not surprisingly, that the population of cars in use worldwide is growing, and that the number of model types and average age is also growing. Interestingly, you can see that the profile varies significantly around the world. For example, North America and Europe have a lower rate of growth in the car population and an older average age, while Asia, and specifically China, have a higher rate of growth and a lower average vehicle age. So what are the implications of this trend? We would argue that manufacturers need to speed and improve their product development process so they can keep up with an increasing demand for automotive aftermarket parts, and to handle the complexity of serving a market with more model types and with major trends towards electric and autonomous vehicles. We also propose that a possible solution for manufacturers to react to these trends is for them to implement an integrated solution for product development that creates a digital twin of the product, a process that adds data to the digital twin and leverages this data throughout the product lifecycle. The digital twin can be used to optimize both the final product and the product development lifecycle. The second trend we see and we see this across many different industry sectors, not just automotive aftermarket, is increasing end-user demand for custom products that are tailored to meet the requirements of individual customers. Of course, creating custom solutions has for a long time been a focus for aftermarket parts manufacturers. Customers want parts that are robust and reliable, but also ones that enable them to individualize their vehicles. These custom solutions may increasingly be connected to each other and to the internet, and they may contain more electrical components such as sensors, processors, and actuators. An implication of this trend is that manufacturers need to become more customer-centric and enhance their approach to customer segmentation and experience. They need to be more flexible and react quickly to changes in customer demand and to meet individual requirements. A possible solution to this trend is to develop a more flexible product development process that can easily create multiple options and variants of standard products. Also, managing specific customer requirements alongside the product development process can help manufacturers meet customer demands more effectively. In addition, the opportunity exists to quickly create photorealistic renderings and animations of products to support sales and marketing, together with the ability to supply data and product images to quickly populate online catalogs. The third trend we see is that new design and manufacturing technologies are providing entry points for startup manufacturers, and that this presents both threats and opportunities for more established manufacturers. Some of these new technologies include reverse engineering, generative design, and additive manufacturing. Reverse engineering may not be a new technology, but new capabilities in capturing physical data using low-cost devices, creating mesh-based CAD models from this data, and then using these models alongside traditional CAD models are having a big impact on users of this technology. The implications of these new technologies for automotive aftermarket manufacturers are that firstly, they need to be aware of the capabilities of these new design and manufacturing technologies, and then move quickly to adopt them when appropriate. And as you can see from this quote, the McKinsey research that we introduced earlier recognizes the threat to existing manufacturers from new entrants who are using these new technologies as their entry point. Some possible solutions from these new technologies include, in the area of reverse engineering, the ability to quickly scan existing components and vehicles and create mesh-based CAD models of these existing components. These CAD models can then be used to speed the design process for replacement and add-on parts and increase the accuracy of these new components. Another rapidly developing technology is generative design. This applies computing power and finite element analysis techniques to the creation of optimized, lightweight parts. The parts designed by this process typically have a more organic appearance, as shown in this graphic. And another possibility from a new technology is the use of additive manufacturing for fast creation of prototype and production parts. Additive manufacturing is a flexible technology that enables you to manufacture parts on demand with minimal investment in tooling, and also has the possibility to enable manufacturers to reduce the need to maintain extensive inventories of little-used parts, as they can be printed on demand. As we mentioned earlier, Siemens proposes that manufacturers speed and improve their product development by creating a digital twin of their products. The digital twin can be used as the basis for many areas of product engineering, including managing customer requirements, product costing, concept and detailed design, simulation, manufacturing, and creating technical documentation and photorealistic images. Data is added to the digital twin throughout the product lifecycle, and this data is used to improve the performance of the product itself and the efficiency of your product development process. At this point, we would also like to introduce Solid Edge. Solid Edge is a portfolio of solutions aimed at speeding product development for startups, small and medium-sized manufacturers, and departments of large enterprises. Smaller manufacturing companies do not typically have the high-end IT resources of larger companies, and solid edge solutions are designed to meet the needs of these manufacturers by being easy to access, implement, and use. The solid edge portfolio includes solutions for concept and detailed mechanical design, electrical design, simulation, manufacturing, technical publications, data management, and cloud-based collaboration. The solution examples in the remainder of this presentation are all from the solid edge portfolio. Solid edge has been deployed successfully in a wide variety of automotive aftermarket and supply chain manufacturers. Some examples include steering and suspension components, powertrain components, kit car manufacturers, components for off-road racing, automotive seating, specialist vehicles, automotive assembly tooling, and startup automotive components manufacturers. All of these images are from published case studies that document the benefits these manufacturers are achieving using solid edge. Diving a bit deeper into the needs of automotive aftermarket manufacturers, we have identified 12 key product development processes that are critical for success. All of these are supported by and improved by creating a digital twin of the product. These processes start with the ability to visualize new products before they are manufactured, creating attractive photorealistic images and animations to support your sales and marketing efforts through areas like detailed mechanical design, optimization, integrating electrical components, collaborating with suppliers and customers, and creating documentation to support manufacturing, installation, and maintenance. As we have limited time today, we will take a look at 4 of these 12 key processes: speeding mechanical design, optimizing for weight and strength, reusing data from suppliers and current vehicles, and collaborating with suppliers and customers. Mechanical design is a core process for product development, and there are several 3D CAD solutions that do a good job of creating accurate 3D CAD models of parts and assemblies, and if required, also creating 2D drawings. Solid Edge has unique capabilities, including synchronous technology that helps speed the design process, and that also help you make design changes and reuse existing design data more easily. If you search on Solid Edge ROI Calculator, you can access a tool that illustrates the time savings you can achieve in your product development lifecycle. We've recently added a new technology for creating complex surfaces in Solid Edge. This is called subdivision modeling. It's a great way to quickly create aesthetic, smooth forms. With subdivision modeling, you start with a basic mesh and then use a polygonal control cage to create your desired shape. You can subdivide surfaces and create finer meshes in specific areas to create specific features. The great thing about this new capability is that it is included right inside Solid Edge, and the surfaces and solids you create using this technology can be used in the downstream operations that Solid Edge supports, including photorealistic rendering, stress and fluid flow analysis, creating toolpaths for NC machine tools, and creating technical publications. One area where we feel Solid Edge is differentiated from other 3D CAD solutions is that it includes unique convergent modeling capabilities. This technology combines design information stored in mesh-based models, for example, data created during reverse engineering and that used for additive manufacturing, with that stored in the boundary representation format that is traditionally used for defining 3D CAD models. This means that mesh-based CAD models that are created by some of these new technologies, including reverse engineering and generative design, can be used alongside CAD models created using traditional boundary representation techniques. This in turn improves your flexibility and speed during product development. Let's explore the area of generative design in a bit more detail. Generative design is one of these newer technologies that create mesh-based CAD models. Generative design applies computing power and finite element techniques to creating designs. The engineer specifies some basic parameters for the design of a component, for example, the space in which it needs to fit, a specific bearing surface and loads, and the material type. The system then iterates through different design geometries to come up with an optimized geometry that has the required strength while minimizing component weight and material usage. This process creates organic-looking components that are well suited to manufacturing using the additive manufacturing process. However, the user can constrain the process to create components with flat surfaces that can be manufactured more easily using traditional machining processes. When designing components for the automotive aftermarket, it is usually necessary to design new components to fit correctly on existing vehicles and existing parts. A couple of approaches can be useful here. You can use reverse engineering to scan existing components or even complete vehicles to capture the geometry into a 3D CAD model that you can then use as a reference for developing your new design. Or if CAD models already exist for the components you need to work with, you can open these directly in Solid Edge. And the synchronous technology that is built into Solid Edge enables you to access the features and intelligence built into CAD models in several different CAD formats. As we mentioned, if CAD models already exist, you can open these directly in Solid Edge. Here you can see the menu of direct file open operations that are available in Solid Edge. You can see that many of the popular CAD formats like SolidWorks, AutoCAD Inventor, and ProEngineer are supported. We also have data migration tools to perform bulk translation of third-party CAD data while maintaining the important links between parts, assemblies, and drawings. In general, Siemens strives to ensure its customers can work easily with CAD data from third-party CAD solutions, and supports many standards that are used in the automotive industry, such as STEP, IGES, and JT Open. Another of the key processes that we will touch on today is collaboration with customers and suppliers. The ability to collaborate effectively is increasingly important as traditional supply chains are under pressure from an uncertain environment around tariffs and from global health concerns. Manufacturers need easy and flexible methods to collaborate with customers and suppliers both locally and globally. Examples of collaboration can include working with a customer who is in a remote location to review the design of a new component, or working with a tooling manufacturer to investigate an issue you have encountered in the manufacturing process. Siemens has easy-to-use cloud-based collaboration tools that enable you to share design data that was created in many different CAD formats with customers and suppliers, and this can be done in a way that protects the intellectual property of your designs. Let's look briefly at a couple of our case studies for automotive aftermarket manufacturers who are using Solid Edge. ACAD is an Italian company that manufactures steering and suspension components for automotive OEMs and also for the aftermarket. They use Solid Edge for fast and intuitive 3D design. They also use Siemens Teamcenter software to manage multi-CAD data and to integrate their design and manufacturing operations in different countries. Reliability of their components is critical for their success, and they use the integrated SimCenter FEMAP solution from Siemens to perform stress analysis on the digital twin of their products to validate performance. Another case study is for this project to reverse engineer the DAX 427 kit car. In this case, some 2D drawings were available that were originally used in the design of the car, but in order to communicate complete design information to potential suppliers, it was beneficial to scan key components such as the chassis and body panels and create a complete 3D model of the car. This has made it possible to select the best suppliers for component manufacturing for future kit car builds, and also the creation of attractive photorealistic images that communicate how individual requirements in terms of colors and equipment can be met, increasing sales success. Note that many of the large automotive OEMs are already using Siemens Digital Industries software for body and powertrain design, lifecycle collaboration, and digital manufacturing. For automotive aftermarket and supply chain companies using Solid Edge, this means that data exchange is very straightforward. A key here is that Solid Edge uses the same Parasolid graphics kernel that is used by NX, the Siemens CAD solution that is used by many of the largest automotive manufacturers. Your data and investment in training are future-proofed by using the same data types and standards used by the leading automotive OEMs. And just before we hand over to Craig, here are a few suggestions on how you can find out more. You can go to our website at solidedge.siemens.com. If you navigate to the Industries section, there is a web page with insights specifically for automotive aftermarket and supply chain manufacturers. And you can also download a free trial version of Solid Edge from here. At this point, I'd like to hand over to Craig Hall for his presentation.
Hi, I'm Craig Hall, owner of Hall Designs, a small business based here in San Diego, California. I offer design and procurement services in the off-road industry, specializing in desert racing with cars from the Baja 1000 to Dakar vehicles that race in South America. So many of the OEM builders in the industry don't have dedicated or full-time employees doing CAD work. That's where I usually partner and can step in and offer my experience. I myself have spent close to 20 years in the sheet metal job shop industry and have designed a lot of parts for a lot of different business sectors over those years. My personal involvement in desert racing is what led to my business and being able to offer friends and those OEMs the assistance in taking their hand-built products into a manufacturing level component or complete assembly. A lot of times we'll have to scan using a roamer arm here. We'll scan either a small component or suspension component all the way up to a complete chassis that's been hand-built, that they maybe needed to build a hand-built prototype, or we're making a change to something and we need to take that and get it into a CAD model to base either that design or possibly a new design. We also do a lot of scanning on obsolete parts that are either no longer available from that manufacturer or that builder is simply no longer in business. So here's a few items we have to use in almost every vehicle design we do. So there's a lot of human bodies you can get to take up, the cab space and check all your ergonomics. But one thing we have to deal with in racing is obviously wearing a helmet. This is one of the vendors' kind of standard helmets that a lot of people use, and we have a you can see the microphone and earbud pickup wiring there, and then air vent fitting for a fresh air hose. And we also have a basically it's called a skirt that velcros to the bottom, and you tuck it into your driver's chute to keep dust from coming up underneath the helmet and getting the inside of your lens dirty. And so we have fresh air to keep one, cold air in, but kind of keep it slightly pressurized to keep dust from getting inside the helmet. So this was a scan I did. You can see the mesh file. It's a really uniform mesh. I didn't need kind of any specific parts of the helmet. It was just going to get stuck on my human model, so we just did a quick surface model of it, surface patch. You can see all the individual patches here, but it is a solid, because it's a enclosed solid mesh, that it does become a solid body. It's just surface patched. Another model we use a lot is tires. So usual tire size is pretty important. the vehicles were running 40-inch tires, 17-inch wheels. This is pretty much the go-to tire package. 40 by 12.5, 17, BF Goodrich. So I scanned just enough of the wheel to get the center line, the axis, the mounting surface, the inner bead, the outer bead lock, and then just enough of a tire patch that I can model individual treads and then just revolve it and create a pattern. Now I was able to actually get a CAD model from the wheel supplier on this, so that worked out good, that I'm able to put the wheel in here, and you can see I mated it up exactly as it fits into my scan. But then I was able to do the model of the tire itself. So you can see I modeled just, I think there's two different tread patterns here, two different groups of tread, and then just arrayed that around the entire model. Here's another assembly or model. A lot of the trucks use just a standard, like a 3-speed automatic, the Turbo 400 for those that are familiar, which dates back to, I think, the early 70s. This is a aftermarket case for that transmission. All the internals are, I think there's very few OEM internal components these days, but the external case is a new heavy-duty SFI rated for racing, and just so we're not having to use cases that are 20, 30, 40 years old anymore. So this has a separate bell housing, the case, and then a lot of different variety of oil pans. So we started with the actual bell housing itself and got the bell housing in, because there's a Ford and a Chevy bell housing. So we did this is the standard that almost everyone uses, is the Chevy bell housing. And then we got into modeling the entire case itself. There's a few fittings that we would plumb in and out for the oil lines. There's a lot of electronic sensors, levels, pressures, temperatures, as well as the pan itself. Now the pan on this, there is quite a few aluminum pans that are cast aluminum, but in racing this is mounted as low as we can in the vehicle, and the aluminum tends to crack when you take a hard hit, and maybe it bottoms out or crushes the skid plate, and the skid plate is probably 3/8 half inch away from the pan. So if we can have a steel pan and you're able to beat it up with a rock and dent it, it is a lot less likely to begin leaking with an impact. So this is a large project. You can see I got pretty much every detail in here, but we use this to get our exact driveline locations and just placement of a few small components that bolt to the transmission. Here's a assembly where we use that transmission. This is an underdrive unit that bolts to the back of the transmission to slow down or underdrive the speeds. So this is how the unit comes from the manufacturer. They have their own little mounting plate. We don't use this. We incorporate it into a larger mounting plate of our own. So here is our assembly. So this is a large aluminum plate that is machined and has the mounting bolts that actually attaches it to the chassis of the truck. And then the actual complete unit with the transmission case shown here. So the case is just has a bolt pattern on the back, and the underdrive assembly sandwiches the mounting plate into the case. And we have some quick disconnect oil fittings when we have to swap out a tranny mid-race, which usually takes around 30-35 minutes. So this is some quick disconnects so we don't lose any oil. I have an oil filter here and fittings. A couple electronic sensors here, and not shown are some large charging or power cables that go from the alternator into the chassis. So we run a second alternator on some of the trucks, and it's driven off of just a pulley on the U-joint here. Some of the trucks have dual alternators on the engine package, but with different manufacturers of engines, that's not available on everything. So this is how we go about mounting an alternator on a few of these trucks. Another component we use a lot is a seat. So a seat is, again, another item that we can't get from a vendor drawing of. So this was a scan of a Sparco seat. It's a newer QRT seat. You can see again here is the mesh file, and basically we need probably the mounting points and just the outside shape. Again, I'll put my human body inside of this to take up vehicle space, and a lot of clearance issues, not issues, but we just got to be aware of the shoulder area on the seats on tighter, smaller vehicles. And then here is my finished CAD model. It's a solid model, surfaced, and basically, of course, we can cheat here and just do half of it and then mirror it to the left or right side, whichever. I think I did the left side here, but here's our basic two-wheel drive trophy truck. A trophy truck is our unlimited class. Besides a few safety restrictions, it's unlimited in horsepower, wheel travel, tire size, 2 or 4-wheel drive, in multiple kinds of body configurations, or whatever you want it to look like, basically. So these are kind of a traditional driveline layout, front engine, transmission into regular drive shaft into a traditional straight axle rear end. Most of the trucks these days are two-wheel drive, mainly for just reliability of components. The four-wheel drive is, well, it might have a little more traction. We're really racing across the open desert, so there's very few instances where you have slow speed. But in the past 5 or 10 years, the level of competition has gotten pretty even. All the components are available to all the teams, and it's just kind of created just an opportunity for people to come up with, a few small tweaks or advances in driveline, suspension. This here on one team was a new engine package, and it was actually a Joe Gibbs engine package. Big 1100 horsepower. That's fairly new in the past, about 3 years with desert racing. But because of this level playing field, teams are wanting to find that next advantage, and really they're looking at four-wheel drive again. A few other forms of racing have been developing heavy-duty front driveline components. Most of these guys are like rock racers. They race King of the Hammer type race, where it's a race course that's anywhere from 30 to 100 miles long, but they are racing through the desert and then partial rock terrain, which has giant boulders, and their co-riders actually getting out and using a winch to help them get through certain areas sometimes. So because they are four-wheel drive, they've been going through teething issues of front drive line and hubs. So they've developed better products because of that. So a few of those products are carrying over now to desert racing and teams wanting to build four-wheel drive trucks with the same wheel travel and horsepower that we have in desert racing. So one of my customers, Camberg Engineering out of Huntington Beach, California, who I've worked previously on other truck designs, approached me about a new all-wheel drive truck. You could see here right away that it is a mid-engine platform, the engine being behind the traditional transmission. This comes down to packaging with the front drive line. You see the transfer case into the front differential, both X-Track units, and 3-speed automatic shown there. And we also have a couple different manual transmissions placed in there as well to confirm fitment and give options on depending on what a customer would want. So we started out with the base wheelbase and track width as previous trucks, and the rear suspension geometry, making a few adjustments to the rear and quite a few adjustments with the front based off of basically the CV joints, and those being your limiting factors for both wheel travel as well as steering angle. So there's even as large as these trucks are, they're still very tight fit with the shock to both the axle shaft, the upper arm, and even a few other little small components around the control arm, and even the tire at full lock. It's definitely a lot of work to package all the components, and there's a little give and take on what you would like, but the four-wheel drive definitely throws a different mix into the package. So one of the first items we needed to model was the front suspension upright and hub package. This being all-wheel drive and A-arm, we had to accommodate a CV joint, and we were also using a portal gear design, which essentially moves the output down about 5 inches from the input. You can see the additional height or offset gained there with the portal gear set. The portals themselves aren't new. They've been used in military and agricultural vehicles for probably at least 50, 60 years now. It's a pretty tight package, fitting all the components. That's a 17-inch wheel, clearance with a few fittings and vent lines. That's a 14-inch brake rotor, so that's a tight fit with the caliper onto the wheel itself. You hide the caliper and rotor and hub here, and two-piece design with the cover. So the cover removed, you could see the 4-gear design has an input gear on the stub axle at the CV, and then 2 idler gears, and that transfers down to the drive gear itself. This is the same rotation, so it's kind of nice that we don't have to deal with anything having reverse rotation as far as our transfer case or in the differential. So it has a traditional drive plate, like on a full floating axle that connects to the hub, and then it has a broached spline section on the drive gear that it attaches to. This is not even a new design in desert racing. There is a similar design, but the overall concept is definitely new. All the gears and hard driveline components are made for this specific package. The drive flange there, and the gears, the stub axle. The bearings are mounted on both sides of the gears, so the cover and the housing both have the same bores for the bearings. The cover also has the studs for the caliper, so we also incorporated dowel pins into the cover to keep that alignment where we needed it for the gears. A few other things stuffed in here. You got a couple sensors. You have a speed sensor, oil temp sensor, there's a drain, there's a fill, a vent line that pokes through the side and into the back half. Going to a section view, you could see just how close everything is. We have a traditional snout with the wheel bearings for the hub and then the bearings for the gear set themselves. Once all this was done, we could kind of move on to some of the other components on the chassis itself. So with this not being the normal two-wheel drive upright that we've done in the past and being definitely a lot more complex upright design with being a four-wheel drive, we thought it best to go ahead and 3D print the entire upright. Here's the base housing itself and part of the cover. Didn't have the both halves of the cover, but the top half, and also the stub axle, which had the CV and the input gear on it. You see the bores for the two idler gears. But this allowed myself and my customer to go over a few of the design features that we were looking for and possibly had questions on. Checking clearances for hardware and some of the other things that it was just a lot nicer to be able to see in person versus on the computer. This also allowed us to go over things with our machinist, who will be doing this in a 5-axis machine, but it's still a large, complex part. It's about 22-inch tall, about 13-inch wide. But this does allow even the machinist, even though they have a CAD model, to kind of take a look at it and be able to see what would be the best way to fixture and kind of attack the milling on it, because there is quite a bit of work to machine this out of one solid chunk. That chunk will be about 110 pounds. And we're going to machine away just over about 75% of that, getting down to our final product here. But this 3D print allowed myself and my customer again to get a good visual on the final product and make sure we're both happy with the looks of it before we let the machinist loose on it. Now I'll hand it off to the host.
Thanks again to our presenters today, Mr. David Chadwick and Mr. Craig Hall, and thank you all for joining. With that, the session is closed. Goodbye.